All right, so we're going to go answer our questions based 16 to 20 on the information below and on your knowledge of Earth and space science. And some questions may require the use of the 2024 edition reference tables. Okay, so I'm doing a quick scan, stars in the Big Bang, model of life cycles of different stars. So 16 says, identify the factor that determines the lifespan of sun and other stars, right? So I'm gonna do a quick scan, right? And do I see anything that lets me know about what determines the lifespan of the sun and other stars, right? So while I'm scanning, I don't necessarily see too much information about the life cycle of stars, but I look at this model right here, and I see they've broken up the category into low mass stars, right? And in, well, red dwarfs, and they live on for trillions of years. I see medium mass stars, our sun, and I see the lifespan billions of years, right? So I'm definitely highlighting any information about lifespan. And I see for high mass stars, I see in millions of years. So these three represents my different categories of lifespan. And how are these categories separated by? I see low mass stars, medium mass stars, high mass stars. So what's the factor that determines whether a is going to live on for trillions of years, billions of years, or even millions of years? It's the same factor that is separated by these three categories: high mass, medium mass, and low mass. So that means that the factor must depend on the mass of the star, or if you wrote just mass. All right. Another thing you could have done to that where the reference tables could have helped you is the fact that I see about the lifespan, right, or life cycle of different stars. I can go on my table of contents and I see life cycles of stars model. And so when I go to page 5, I see right here the life cycle of star models. And the early stage, they all start off protostars, but you see it says massive stars and sun-like stars. So that lets me know even here the pathway have split based on the mass of the star. All right. So that's why answers would be mass of the star, or you could have said mass. All right, so number 17, right? It gives us a table below, shows some information about different types of star. Solar mass is the mass of the star compared to the sun, right? We have this data table. And it says a student created a data table containing information on how stars synthesize common elements through nucleosynthesis. Which row of data correctly identifies all the characteristics for that star? So we're going to do a process of elimination with some things that we don't know, right? That we do know. Now, keep in mind, right? Remember, for this cluster question, it's 16 through 20, and that means we can use all the information, reading diagrams, even from different questions within that cluster that can help us. All right. So when I'm looking at this characteristics, I don't see anything yet that can fully relate to nucleosynthesis, right? But I do see star name, right? I see lifespan, right, that can match up just by that alone. And I see something about solar mass, but I'm going to get to. So I see our sun. We're gonna skip the nucleosynthesis for right now, right? And it says it's a medium mass, right? And it's a lifespan of 4.6. So when I look at my sun, it has a solar mass of 1, right? So, and it has a lifespan of 9 billion. but it says lifespan of 4.6. So it can't be choice one, right? And did I see anything that's mentioned about medium mass, high mass, medium mass, and high mass? I do remember these terms when I look right here in this model, right? Remember, we see high mass, medium mass, and low mass. And so, medium mass, like our sun, for example, right? That represents a medium mass. So, keep that in mind. When I take a look at two, Sirius B, right? It says carbon to oxygen, and it says it's a high mass and a lifespan of 0.23 billion. So, Sirius B, I see here, but it says the lifespan is correct, right? But the solar mass is what's throwing me off. Because if the sun, according to what we just saw, is a medium, sorry, no, we can't see it. If the sun is a medium mass star, how is Sirius B, which has a lower solar mass, how can that be a high mass star? So it can't be a high mass star, right? Now I see Aldebaran, right? The mass as a medium mass, let's see, it says 1.16. Okay, so that's something that might end up fitting the range, right? And I see the lifespan of 6.4. The 6.4 is correct, right? So this may possibly be an answer. Let's look at Wolf 359. Wolf 359, it says it has a high mass and a lifespan of 4.1 trillion, right? Well, when I see the solar mass says 0.09. So even though the lifespan is still correct, 0.09, it can't be high mass if a medium mass is 1. So it definitely can't be that, right? Now, let's say, for example, we had another option that gave us correct, let's say like correct mass and lifespan. And how would we then know, right, if the nucleosynthesis is correct? Well, we know that in the beginning or main sequence stage, hydrogen does fuse to helium, right, for a main sequence star. How do I know that? Because if we go to our reference tables, and I want us to go to page 2, right, that talks about generalized nucleosynthesis in a massive star, right? Yep. We know the first stage, right, is a stage that any all stars go through, is that hydrogen to helium star, right? But we've also learned once a star runs out of hydrogen, and you look in the problem, right? Look at the medium mass. It says Sun expands and cools and turns to a red giant. So at this point, right, the star has ran out of hydrogen to fuse helium. It'll now begin to fuse helium. So when I look, my next stage is helium to carbon. Helium to carbon. And what do you notice? Right? Even when I go to my problem, look at my nucleosynthesis, the synthesis, sorry. Helium to carbon. So that just confirms that choice three is the correct answer. But once again, this is a question that you can do the process of elimination. All right, now we're gonna look at 18. So it says sunspots, right? It's a reading about sunspots, right? It gives me a chart, oh sorry, a graph about the solar cycle and the number of sunspots recorded. And it says using information from the passage and the graph. So this is purely from using information from the passage and graph, not necessarily a content question. It says place a check mark in three boxes. So that means even if you place a check mark in just two, you're not going to get correct. You have to have three check mark boxes to identify the statement that accurately describes sunspots. So we're going to go through each one. It says a decrease in the number of sunspots is inferred to decrease Earth's temperature. So I'm going to go on my reading and I'm going to see if there's any reading that talks about between sunspots and inferred to decrease Earth's temperature. Okay, so when I scan, it says sunspots are areas where magnetic field is about 2,500 times stronger than Earth's magnetic field. You can pause the video and read this yourself before I go through it, just because I'm just scanning. So I'm scanning about something regarding sunspots or something about temperature. All right. So it says because of strong magnetic field, the magnetic pressure increases and the sun's surrounding atmosphere pressure decreases. This lowers the temperature, okay, let's see, relative to the surrounding areas. Okay, because it inhibits the flow of new superhot gas to the surface. Okay, so this is a sentence for me to keep in mind that I may have to come back to. All right, once again, looking in regards to sunspots and temperature. Sunspots occur in pairs because they have magnetic fields pointing in opposite directions. However, 6:45, 17:15, there was near zero sunspot activity. From 1645, there was nearly zero sunspot activity. This time period is referred to as the Maunder minimum. Some scientists also call this time period on Earth the Little Ice Age. So this time period, 1645 to 1715, they called it the Little Ice Age, right? Any period that's referred to Little Ice Age must refer to cold temperatures. All right. And they said during this time period, what was the sunspot activity? It was nearly zero. So when I'm looking, nearly zero sunspot activity, Little Ice Age. Nearly zero sunspot activity led to Little Ice Age. So a decrease in the number of sunspots, right? No, nearly zero sunspot activity inferred to decrease Earth's temperature. They said this time period on Earth is called the Little Ice Age, right? This means that there was cold temperatures taking place on Earth. I would check that. That's one. The number of sunspots changes each year, occurring in approximately 11-year cycles. So I'm going to look at my graph. Does it look to be that my cycles repeat itself about every 11 year? All right. And approximately, right? Approximately, which means that it has to be close to 11 years. Means that there's some cycles that may be 12 years. Some cycles may be 10 years, but it rounds to about 11 years. So I'm going to pick a point on the graph, right? A low point, 1955 or so. The next time that I see it, it looks to be about 1965, right? I see about a 10-year difference. All right, the next low point, 1965, and it looks to right here, looks like 1977, maybe about a 12 year, right? Then 1977 to it looks like about 1987, looks like another 10 year, 1987, and it repeats itself again to about maybe 1997, right? Or so, 997, maybe about another 10 year, 1997, and this goes all the way to, it looks like 2008, which is the last year. So 1997 to 2008 looks to be about 11 year. Could we say approximately, right? Meaning that it can be close to 11 year, right? Could we say that the cycle repeats itself, right? approximately 11 years, right? Meaning that it doesn't have to exactly be 11 years, but it has to be close. I see 10 year, I see 12 year, I see another 10 year, another 10 year, I see another 11 year. So yeah, I would definitely say that. All right. And if you just know anything about sunspots, right, as a content question, they usually occur in 11-year cycles. All right. An increase in solar output is associated with a decrease in the number of sunspots. Let's see if the reading talks about that. It says sunspots are where magnetic field, the pressure increase, decrease is lower because of hours. Sunspots occur in pairs because they have magnetic fields pointing in opposite directions. So it looks as if the magnetic field is strong, strong magnetic field. Based on the reading, increase in solar output is associated with a decrease in the number of sunspots. Um, I don't necessarily. I know in the content question, right? I would know what the correct answer is. But just looking on the reading, right? They tell us the number of sunspots. I don't necessarily see anything in regards to solar output, right? So that means that, okay, you know what? I'm a little bit shaky, right? So I may not pause this. I may have to come back to this, right? It says the average number of sunspots appearing each year has decreased steadily since 1950. When I take a look, right, and let me erase all this other stuff, right? And when I take a look, since 1950, which is right here, it says sunspots have decreased each year since 1950, right? Well, it does decrease, but then it shows an increase in this area, right? It's showing another decrease and then a slight increase, right? And then even after that, it begins to generally increase in general. So is it really decreasing every year? No. So I know this definitely can't be the case, right? Now, this last one. Sunspots are regions of cooler temperatures on the surface of the sun. Does the reading tell me anything about temperatures that are cooler on the sun, referring to hotspots? Well, I underlined quite a statement about temperatures, right? It tells me about sunspots are areas where the magnetic field is about 2,500 times stronger than Earth's magnetic field, right? Because of this strong magnetic field, the magnetic pressure increases and the sun surrounded atmosphere pressure decreases. This, right, which is referring to the magnetic pressure, right, in the magnetic field, this lowers the temperature relative to surrounding areas, right? The surrounding areas they're talking about is the sun because it inhibits the flow of new super hot gas to the surface of what? The sun. So it tells me right in this sentence that this, right, where we're talking about sunspots, right, this lowers the temperature relative to surrounding areas. So that's definitely a stronger answer than this answer over here. So that's why we have our three checks. All right, number 19. It says the relationship between galaxy distance from Earth and recessional velocity graph shows that the recessional velocity of a galaxy blank as a galaxy distant from the Earth's increase. So we're going to be filling in this blank, and it says which table correctly identifies the missing words and phrases labeled A, B, C, and D in the passage above. So we see the relationship between galaxies' distance from Earth and recessional velocity, right? So number one, we definitely have to be able to look at some background information. All right. So it says in 1920s, Edwin Hubble studied the motion of galaxies. He found a relationship between a galaxy's velocity as measured from Earth, which is called the recessional velocity. So recessional velocity is a galaxy's velocity as measured from Earth and the galaxy's distance from Earth. This relationship is known as Hubble's law. The law has implications for understanding how the universe has changed since the Big Bang. The graph shows data on several galaxies' distance from Earth in megaparsecs and their recessional velocities. So once again, I see this word recessional velocity, and we have to remember that recessional velocity is a galaxy's velocity as measured from Earth. So we are understanding the speed of a galaxy, measuring it or comparing it from Earth. All right, so keep that in mind. And so we see, right, as the distance to the galaxy, distance from the Earth to a galaxy increases, right? We see the recessional velocity also increases. So it does look as if the speed is getting faster and faster and faster, right? The speed is getting faster. Okay, keep that in mind. So it says that the relationship between galaxies' distance from Earth and recessional velocity graph shows that the recessional velocity of a galaxy is increasing proportionally or not increasing non-proportionally, right? When we're talking about the word proportionally, we're just talking about is it increasing at a constant rate? All right, is it increasing at a constant rate? So a graph that shows that it's increasing non-proportionally, it'll look like a curve, right? Increasing at a constant rate means it's predictable, right? A straight diagonal line. So keep that in mind. So when I look at that, and I see that it's increasing at a steady or constant rate, right? A steady or constant rate. Therefore, I could automatically cross out which option? 4 and 2. All right. So let's keep going. So we know that A is going to be increased proportionally as the galaxy distance from Earth increases. This is evidence for the expansion of the universe. One and three both have expansion, right? So we know B is expansion of the universe that suggests this is evidence for the expansion of the universe and suggests that the universe was blank. Was it initially inflated or was it compacted? This is, let's say, this is more where it's a conceptual sort of question, right? In your homework, you've done some reading about the Big Bang Theory, right? And one of the things that it talks about is that the universe started 13.8 billion years ago and was an extremely hot, dense point, right? It was an extremely hot, dense point, and then it expanded rapidly, okay? Conceptually speaking, right? And one of the things in this review sheet, right? You could even see, right, from the moment that the Big Bang happened, it talks about how the evolution of the universe is expanding, right? And as time passes on, right, it's even expanding even at a much faster rate. So that's why even by me looking, right, initially the universe was, as we said right here, it was an extremely hot, dense point, right? So that's why, in this case, not an inflated, but a compacted at the time of the Big Bang. And as a result, this data suggests that the universe is changing at an accelerated rate, right? The universe is expanding, right? The universe is growing bigger and bigger, not at a decreasing rate. It's not slowing down. It's actually speeding up the expansion rate. That's why the correct answer is choice one. All right. It says, based on the information from the relationship between relative amounts of different particles and temperature of the universe after the Big Bang over time graph, which table correctly identifies a composition of matter in the universe as evidence for the Big Bang theory? So when I'm looking at this graph, you may be looking at this graph and you're just like, I have no clue what I'm even looking at, right? So one of the things, maybe this reading will give me some idea. So it says particles were created as a result of the Big Bang. The first particles were subatomic particles like the protons, neutrons, and nuclei of lighter elements such as hydrogen, helium, lithium, and beryllium. The graph below, so now it's telling me what the graph is showing me. It's showing me some information about these particles, the temperature of the universe at the time they were created, and the amount of time after the Big Bang that they were created. So it's showing me three pieces of information: temperature of the universe at the time they were created, information about these particles, right, which were hydrogen, helium, lithium, beryllium, right, protons, neutrons, nuclei, and the amount of time after the Big Bang that they were created. So this chart is separating the three things from the graph, right? Time, particles present, and the temperature. So I'm looking for which one is true, all right? From 10 to 100 seconds, H and HE decrease. Let me see if that's true. From 10 to 100 seconds, and let me even zoom in right here. From 10 to 100 seconds, so I'm only looking at this area right here. It says H and HE decreased. Okay, H and HE decreased. Well, remember, H refers to hydrogen, right? That's the chemical symbol for hydrogen. And He, chemical symbol for helium. And it says, so hydrogen and helium decreased. Is that true? Did these particles decrease from 10 seconds to 100 seconds? Hydrogen, the line is going up, so it increases, right? For hydrogen. Helium, right? And I see multiple different types of helium, right? But both of these lines here, right? And even here, they're all increasing from 10 to 100 seconds. The line is going up. So it can't be that. It can't be that. Let's look at two. From 100 to 1,000 seconds, H increased, then decreased, right? While He, helium, increased and then remained constant. And the temperature decreased. Let's see if that is true. All right. So I'm going to erase right here and I'm going to go from 100 to 1,000. All right. I know my, all right. And I'm looking at helium, right? And hydrogen, these lines. Okay. So it says, let's look at helium first. I'll do it in blue. I'm going to highlight hydrogen, which is this blue line. I know it's not the best. And this blue line right here. All right. And let me just fix this line just to make it more straight right here. So when I look at H, right, it says H increase and then decrease. So when I look at my hydrogen lines, right, it did increase and then it's decreasing. Hydrogen increase and decreasing, right? So that checks out for hydrogen, right? Now I'm going to pay attention to my helium, right? My helium line, okay? Let me let me erase so that way it's not the same color. So that way we're able to see. So I'm going to make my helium line green, right? So for helium, helium refers to this green line right here, right? And I see helium again, the green line right here. Okay? Now, what do I notice about helium? During these two areas, and let me use the red as my cutoff point. So from 100 to 1000. Look at my green line. Helium does increase and then it stays on a straight line from 100 to 1000. Helium does increase, but then it stays on a straight line. So does that match up? It does, right? H increase, then decrease, right? While He increased and then remained constant. So we cleared that hydrogen increases then decrease, and we also cleared that helium increased and then remained constant, so straight line. And does the temperature decrease? Well, take a look. As look at our temperature numbers, okay? It goes from, I don't know if people can even see this, but it goes from 10 to the 9, 10 to the 9, and 10 to the 8, 10 to the 8. Then it goes from 3 to 1, and immediately when it goes from 10 to the 8, 3 to 1. So the temperature is getting lower as you're moving to the right. So it checks off, and that's why choice 2 is the correct answer. When you match the other ones, you'll realize that it doesn't match up the same way. All right. So that's all we're doing for this problem is just checking to see which option is correct. All right. So it says, base answers the question 26 through 30 on your information below and on your knowledge of earth science. And some questions may require the use of the reference tables. All right. So, right. And if it's short readings, okay, I can definitely just do a quick scan, right? The sun and eight planets in the solar system formed at the same time. Evidence of their formation can be found throughout the solar system. Scientists have used data from planets, meteorites, and Earth to determine how the solar system formed and its early history. The data table below lists some information for the eight planets. So they give us, right, there's two types of planets, terrestrial planets and Jovian planets. All right. It says, which statement best describes the differences between terrestrial planets and Jovian planets in the solar system as a result of the early history in their formation? One of the things when I'm looking at this option, right? One of the things I see terrestrial planets have longer periods of revolution, right? And fewer moons, fewer moons than Jovian planets. I apologize. Um, so let's go through, right, each one. Let's go through each one just to see what are some things that we can quick check right away. So it says terrestrial planets have longer periods of revolution and fewer moons than Jovian planets, right? Now, this chart does not tell me anything about longer periods of revolution, but the reference tables does. But we're going to get back to that, right? So when I'm looking at terrestrial planets and I'm looking at their moons, right? Do they have fewer moons than Jovian planets? Yes, it looks like they do, right? Fewer moons. So this can potentially be an answer. Um, Two, potentially, right? Terrestrial planets have greater densities and longer periods of revolution. This chart doesn't tell me that, which means I may have to go to the reference tables, so I may have to go back for choice two. Terrestrial planets have larger diameters and are closer to the sun than Jovian planets. Once again, I'm gonna have to check that. And terrestrial planets have small diameters and greater densities than Jovian planets. So, when I'm looking at the solar system data, I'm going to have to use my reference tables. And what page gives me information about the solar system? When you go to your table of contents, look right here. Solar system objects data table, choice two. When I take a look, I saw something about period of revolution, right? I saw something about distance from the sun. All right. So there are things that we can use to help us out here. All right. So first, terrestrial planets have longer periods of revolution than Jovian planet. Well, I'm gonna look at these first four terrestrial and I'm gonna compare it to Jovian planet. So when I go to my reference tables, all of my terrestrial planets I'm going to circle in blue that I saw, right? And I'm just gonna write T for terrestrial. And I'm gonna put red for all my Jovian planets, Jupiter, Saturn, Uranus, and Neptune. Okay. Now, when I'm taking a look, right, I'm looking at what do they tell me to do? Longer periods of revolution, terrestrial planets. Is that true? When I look at just the period of revolution, right? I'm gonna look at, let me circle this in red. These are my data for period of revolution, and this is my data, oops, for my terrestrial planets, right? You'll notice, right, the red data points which represent Jovian, they're all longer than the blue, right? Y represents Earth years, D represents Earth days. So Jovian planets actually have a longer period of revolution. So it can't be that. All right. Um, it says terrestrial planets have greater densities and longer periods of revolution than Jovian planet. We just proved that for choice one. You see, we just proved that. So that means it definitely won't be that as well too. Now let's take a look at three. Terrestrial planets have larger diameters and are closer to the sun than Jovian planet. Let's test that out. Do they have larger diameters? Right? Let's take a look. Look at equatorial diameter now, right? Look at equatorial diameter. And once again, I'm going to highlight, let me erase period of revolution, right? And I'm going to highlight the diameter in kilometers. I'm going to circle for blue for all of them. And I'm going to circle in red, right, for my Jovian. When I take a look, right, the Jovian planets have a much larger equatorial diameter than the terrestrial planets, right? And so we not only did we check that out, but closer to the sun. Let's see if that's also true. If you notice, right, besides the Earth's moon, the celestial objects are listed in order distance from the sun, right? Look at the distance from the sun from the Jovian planets, I circled in red, and look at the distance from the sun for the terrestrial planets, I circled in blue. The Jovian planets are farther from the sun than the terrestrial planets if you're looking at their numbers, and you can pause as well. So they're not terrestrial planets are closer to the sun. They are. That is true. They are closer to the planet, right? They are closer to the sun. That is true. But they do not have larger diameters. And so that's why the correct answer is choice four. Terrestrial planets have smaller diameters. We prove that right here. Terrestrial planets' diameters are in blue. They're smaller number than the Jovian planets, right? And now a content piece of information, right? Terrestrial planets have greater densities because terrestrial planets are considered rocky planets. Jovian planets are considered gas planets. And as we know, gas is less dense than a solid, right? All right, now we're gonna look at number 27. Okay. So number 27 says, which value would be the most accurate prediction for the period of revolution for Saturn? Right? Well, period of revolution, I know that this term I have seen in the reference tables and for Saturn. So let me take a look. Period of revolution for Saturn. Let me erase all this other stuff. Here we go. And Saturn is located right here. Period of revolution, and it's 29.5 years. What kind of years? And this is key. This is Earth years, right? Earth years, right? So it takes 29.5 Earth year. How long is one Earth year? You can either use this value or you just know it. In general, one Earth year is 365 days. So that's something we have to keep in mind. So Saturn has a period of revolution of 29 Earth years. But our job is to convert 29.5 Earth years to turn it into Earth days. Well, what do I know? One Earth year is equal to 365 Earth days. All right. 365 Earth days. If you wanted to be accurate and you wanted to use 365.26, you could as well too, right? So if we know one Earth year is 365 Earth days, and we know that Saturn takes 29.5 Earth years, then we have to multiply 29.5 times 365, right? And when I go to my calculator, 29.5, oops, nope. 29.5 times 360, oops, nope, nope, nope. 365. And what do we get as an answer? 10,767.5. So I got an answer of 10,767.5 days. All right. Now, which answer is closest to that? Which is the closest to this response right here? Choice two. All right. That's all. Make sure to like, share, and subscribe. And for those who have assigned this in class, make sure that you are checking your answers and the questions that you got wrong. Look at the video. All right. And make sure you have your reference tables next to you as well as your notes. Have a wonderful, blessed day.